crossing during meta-domination is that your potential, your growing solution for the potential is essentially just 9 tenths of the primordial one. And there's one more thing you can do using the Poisson equation, to come to the conclusion that meta-perturbations must evolve like the scale factor during meta-domination, which is optimal growth. You cannot do better than that. Okay, you cannot grow faster. You can only grow slower than A at any other time. Okay, now then let's move on to the next approximate solution that we can construct, and that is horizon crossing during radiation domination. Well, here things are totally different, and that is because now instead of having nice cold dark matter, what you have dominating the energy density and the energy density perturbations are the photons. Okay, so as first approximation, what we can do is to set the dark matter densities and at the background level as well as the perturbation level to 0. Okay, and in that case, I just have to worry about what my photons are doing as described by the set of equations for the photons in the tightly coupled limit. And we also have a couple of equations here that are just Einstein's equations. Okay. Now, so the trick is the same, really. We have a couple of differential equations that are first order. Okay, delta gamma dot, and then you have the velocity of the photons dot as well. The trick is to again just combine these equations into, you just go do a bit of calculations, but the trick is that you just combine these things together in order to form a second order differential equation for some quantity. In this case, we want to form a second order differential equation for phi, okay? And so we can do that. Actually, I'm not going to bother doing the actual calculation itself because it's just tedious, but as we saw earlier, for the case of horizon entry during meta-domination, this kind of thing can be done, okay? So we're just going to assume that it can be done and someone's done the work. What you actually end up getting, if you did that, is an equation that looks rather simple. Okay, so you have phi double dot, and then 4 divided by the time, conformal time eta, and then phi dot, plus some k, that should be square, not cube, sorry, 3 times phi is equal to 0. So, having this equation of motion, then the next thing you can do is, well, you can either stick it into Mathematica and solve it and see what you get, or you can massage it into the right form and look it up in a table. Either is fine, but let me just tell you what a solution looks like if I plug it into Mathematica. It looks like this. Okay, so what I'm plotting here is phi normalized to the primordial value, in case the initial value that we have. And what you see here is that, well, it's a very neat, actually, expression you can write down. It's essentially just a spherical Bessel function of order 1, okay? And if you look at the curve, what you find is that you start off at 1, which you should, because the mode is initially outside the horizon, right? And you're entering the horizon during radiation domination. So the initial value is just the primordial value of phi, okay? And it remains at close to 1 while it's super horizon. But once you cross the horizon, here happening here at k eta is equal to 1, and you're sub-horizon, and suddenly the function plunges down. Phi plunges down to 0, and then oscillates around 0. Okay? So in other words, phi decays as soon as the mode enters the horizon. And the physical reason why that is because you have radiation pressure. Okay? Now remember that we looked at the photons equations of motion, and I told you that if you are in the tightly coupled limit, then essentially what would happen is that all your higher multiples will be forced to 0, will be damped to 0. And the only equations that are left L equals 0, the monopole, and L equals 1. And so you just have these two equations that couple together, and in the exactly tightly coupled limit, you have this nice acoustic oscillations at the sound speed of an ultra-relativistic fluid. Okay, so these perturbations are not growing. They are just kind of, going positive, negative, so on and so forth. And now I stick that, acoustic oscillations basically back into my description over here, and the effect it has on the potential is that the potential just dies away. It's not even able to grow, okay, because the pressure doesn't allow it to grow. Okay, so that's the physical reason why it is you have this sudden decay of the potential across upon horizon entry. Okay. The oscillatory bits here are, well, obviously because you have the acoustic oscillations. Okay? So, that's good. Now, these are just, I arrived at this solution by solving just the equations for the photons coupled with one of the scalar Einstein equations. I didn't put in the dark matter density at first approximation. Okay, but now having calculated what we expect the potential to do across the horizon, what we can do now is to examine the system again. Okay, examine in particular what happens to the cold dark matter density, and ask if the cold dark matter density was to evolve in a universe where the potential has to decay away across the horizon, what is it going to do? What is my dark matter density going to do? Okay? So in other words, I can solve the delta C and whatever dark matter equation of motion with the potential given by this function as if it was an external potential, just to see how that could influence my dark matter density growth. Okay, so we can do that. Here are the equations of motion for the cold dark matter. Okay, so you have one for the density perturbation and then one for the velocity perturbation, which is the Euler equation if you like. And again, we do the same thing as we have always done, and to turn these two first order differential equations, combine them together into one single second order differential equation for the density perturbation of the cold dark matter. Again, you can try to derive this in your own time. It's actually very easy, just a few lines. And what you find is something like this. Okay, so you have delta C double dot, and then 1 on eta, delta C dot. And on the right-hand side, I have basically lumped all the potentials together and call it a source term. Okay, so the source term here is, well, a bit complicated. You have you second derivative of the phi, and then phi dx, etc. Okay, x here is basically this function, the argument here in the source term. So x is equal to k times eta. Now, so what you can do now, if you like, is to take that Bessel function from the previous slide and then evaluate the source term. Okay, you can do all of that in Mathematica and then solve this differential equation again to see what you get. But let me tell you what kind of answer you would expect without actually solving it. What you would expect if you look at this solution, okay, you solve this in the presence of this external potential, what you would expect in the subhorizon limit is that the delta C should grow like the logarithm of k times eta. Okay, so k times eta is time, k is the wave number as usual, is logarithmic. Now, during radiation domination, there's also a nice mapping between the time eta and the scale factor. So actually, eta is just equal to a. So what you find is that delta C grows like the log of k times a during radiation domination. Okay, so it's just responding to this potential, external potential that we solved for earlier. And as I said, you can either solve this by plugging into Mathematica. You can actually even do it in an analytical way. You construct the equation, the solutions for the homogeneous part of the equation, and then you construct particular solutions given the the source term. You can even do that. It's actually in my notes, so I hope to scan them at some point so you can read them. But anyway, the bottom line is that you have this logarithmic growth with respect to A during radiation domination. And this is to be compared with what we saw earlier for the growth of perturbations during meta-domination, which is just linear in the scale factor. Okay, so what you see immediately is that during meta-domination, things grow nicely and optimally. During radiation domination, your density perturbations in the matter are still growing, but at a much, much lower rate. Okay, and why is that? Well, the physical reason, again, we have to blame it on radiation pressure. Okay, so as said earlier, your photons the photon energy densities are basically just dominating the potential. Okay, and they don't cluster because the photons don't cluster because they prefer to do acoustic oscillations. And since the photons are the dominant source of energy density perturbations during radiation domination, the fact that they don't cluster and don't really build a potential, the cold dark matter, which is subdominant, can't really grow either. Okay? So that's why it is that you see a little bit of growth, so because the dark matter still want to grow, okay? But it can't really do so when the photons are basically forcing the potential to be small. Okay? So that's what we have here. Now, so the last solution we can look at is that of subhorizon evolution. Okay, and again, so here if you're looking at this solution, you will just be looking at how the various modes grow while they're all subhorizon. There's a lot of overlap in that solution with the three solutions, with the two other solutions that we saw before, so I don't want to do it. But let me just tell you roughly what would happen. You will have some kind of logarithmic growth, okay, of the density perturbations in the cold dark matter during radiation domination. And then you will transition to meta-domination as you follow the trajectory. And eventually, these perturbations would also catch up in their growth and they will start growing like the scale factor. Okay? Now, so this is generically what we expect to happen, but still I don't really know I still need to figure out how the transition happens. So in other words, when I write here delta C grows like A, I also tag a little constant in front of it. It's basically a constant that needs to be determined by matching to the solution before during radiation domination. Okay, so I have this behavior at radiation domination. I expect the behavior to change to that, and I have to still have this constant C that I need to determine from matching. Okay. Now, if I did that matching, well, okay, you can do it in a very detailed way, but generically, when I write down delta C is equal to C times A, I would expect this C here to have some kind of dependence on log K, okay? Simply because I had a log K dependence to begin with during radiation domination. So that should be inherited also while the mode is growing during meta-domination. Okay, so that's one thing I can already write down. Now, one more thing I need to point out, and that is this expression here we have is for the growth of the density perturbations in the cold dark matter, right? But I would like to re-express that in terms of what happens to the Newtonian potential, okay? So what I need to do, therefore, is to appeal to Einstein's equation again in the subhorizon limit, okay? So essentially, I need to look at minus k phi, and then, k squared, and then 4 pi g a squared rho c delta C. Right? Now, we said before that, we've seen before that rho bar C goes like 8 to the minus 3. Okay, that's just how the background energy density evolves with the scale factor. And we also saw just now that delta C has a kind of, logarithmic k times A dependence. All right? So therefore, what I'll find altogether is that this is equal to 4 pi g. I have a squared over here, one factor of a that would cancel with the a to the minus 3. And so I'm just left with c log of k, and that's it. And then, of course, I should also be proportional to the primordial value of the potential. Okay, so if I rearrange this now, what I find is that I should expect phi to grow something like, to grow logarithmically k divided by k squared times whatever is the primordial value, which itself may be a function of k. Okay, so that's a generic expectation of what I should expect phi to grow like during matter dominations for those modes that enter during radiation domination. Okay? Okay, so that's good. I have this solution. And what I can do now is to put everything back together. Okay? So now I go to my next picture with all my 4 solutions. So what I'll do is to pick one time that is pretty late, okay, during matter domination, let's say, somewhere here. And as we saw earlier, we just saw just now, I expect phi to go roughly like this logarithmic thing, k squared phi p, for these modes down here that enter during radiation domination. And then earlier on, we had another solution that we figured out, where phi should be like 9 divided by 10, and then times the primordial value for those modes that entered the horizon during matter domination. Okay, so we have these 2 limits. Let's plot it. Looks like this. Okay, so what I'm plotting here is phi divided by the primordial value. It's equal to 9 divided by 10 for these modes. Okay, and then for the modes that are that enter during radiation domination, you have this slope here, which is basically this one on k squared slope. This ratio here of phi divided by the primordial value has a name. It's called a transfer function. Okay, so basically, how is power transferred from the primordial value to a value at a later time? So it's called a transfer function. And the cool thing here is that, well, okay, I only have like these 2 limiting solutions. That's an interpolation, but let me tell you what, all cold dark matter like kind of cosmologies have transfer functions that look like this. You can't get away from this shape if your dominant matter is kind of cold. Okay, they always look like this. Then relating the primordial value of the phi to the matter density at late times is simple. All you have to do is to, well, use the transfer function, relate to bring you from phi p to the present day value of phi, and then apply the Poisson equation to give you to this point. So all these prefactors here are really just coming from here. Okay. Now, at this stage, you might ask, well, I looked at a terribly simplified model with only cold dark matter, right? But but I also said earlier that we have baryons in the universe, and in fact, the amount of baryons is maybe only a fifth, a factor of 5 smaller than the amount of dark matter that we have. So we then ask, what would happen if I was to reintroduce these baryons? Okay. Well, what would happen if I was to reintroduce the baryons is the following. Now, as we said earlier, when we look at the photons, and they're in a tightly coupled state, what they're tightly coupled with, what those photons are tightly coupled with are the baryons. Okay? So if the photons are tightly coupled and doing acoustic oscillations, you should also expect the baryons to be doing exactly the same thing. Okay? So you have acoustic oscillations in photons and acoustic oscillations in baryons. So in other words, while the photons and the baryons are tightly coupled, the baryons don't like to fall into potential wells either. Okay? Their perturbations also don't grow because they're basically dragged along by the photons all the time and can't really fall into potential wells. So what this means is that if I was to replace some of the cold dark matter, which does like to fall into potential wells, okay, with baryons, then the effective gravitational potential that is seen by the stuff in the universe is actually a little bit suppressed. Okay, it will be suppressed by an amount 1 minus Fb, where Fb here is the fraction of matter in the form of baryons. Okay, so this is what would happen when the baryons are kind of forced to be moving along with the photons. Okay. So effectively what it means is that for the transfer function is that so I have two cases over here. The top one here is just cold dark matter, that's the green line that we have seen before. If I was to replace some of this cold dark matter with baryons, what I would expect to see is a slight suppression of the transfer function on those scales that entered the horizon during radiation domination. Okay? And in fact, it would extend all the way to across this line over here to a scale KB. And KB is defined as the co-moving Hubble rate at a time eta b, where eta b is the time at which the baryons decouple from the photons. Okay? So, in other words, what I mean here is that if you're looking at those scales that enter the horizon to the right of this line, those modes are subject to the fact that the baryons are coupled with the photons, so the baryons can't fall into potential wells, whereas those modes that enter the horizon to the left of this KB line here have baryons behaving essentially like cold stuff, and they are able to fall into potential wells. Okay, so you have no suppression over here, but then a suppression over here on the right-hand side for that reason. Okay, so that's what we should expect to see. Now let's move on to the matter power, looking at the final prediction for the matter power spectrum. Okay, so this is how the matter power spectrum is defined. It's essentially just this ensemble average of my matter density perturbations, and P of M here is the power spectrum of matter. And if I was to construct the matter power spectrum out of the quantities that we've seen so far, then this is what I'll have. Okay, so I'll have the primordial power spectrum over here, P subscript phi P. I have the transfer function T. I have to square it because this is essentially square of a delta. When I form a power spectrum, I'm essentially squaring the deltas. And then I have a big bunch of prefactors that just comes from the prefactors of the Poisson equation. Okay? Now, the primordial power spectrum is something that is determined by inflation, and that would in general be model dependent. But the common thing to do, at least when it comes to fitting data, is to parameterize the primordial power spectrum as a kind of power law. Okay? And usual parameterization is essentially this k raised to some spectral index minus 4. Someone's going to ask me why it's not minus 1. I'll explain that in a bit. And so that's for something from inflation. So if I put this expression here now for the primordial power spectrum back into my expression for the present day matter power spectrum, what I find immediately is I should expect the present day matter power spectrum to be determined by the square of the transfer function, and then I'm going to tack onto it k raised to the spectral index ns. Okay, so that's what we should see, and let me plot it. That's what you should see. Okay, so I have this part of the power spectrum where the transfer function is flat, going like k to ns. and then I have this turning point, and then a sudden drop off of the power spectrum again, okay? So something that goes like k as n s to the minus 4. And that's good, because that is exactly what we see if you actually calculate this thing with a code. Okay, now we have explained it with a few equations. So, so what I'm showing you here, okay, I didn't say much about K equality. So K equality, actually, I think I said that before, it's defined as the co-moving Hubble rate at the time of matter radiation equality. And if you assume a radiation content of just photons and 3 families of massless neutrinos, it gives you a prediction that looks like that. Anyway, yeah, so here are some real matter power spectra that I can show you. These are computed with CAM. I made them years ago, which is why I was still using WMAP values. The Planck values are not terribly different anyway. So what you see here are essentially 3 cases, all with the same matter density, omega m, fixed at 0.134. I fixed the spectral index to be 1. The Hubble expansion, reduced Hubble expansion rate is 0.7. I've fixed also the primordial amplitude. And the only thing I varied between these 3 cases is the amount of baryons, okay, in my matter content. And you can see here that the less baryon I have, the more power I have on the small scales, okay? I crank up the baryon content, my power spectrum goes lower and lower and lower. And that is because of what I told you before about how during radiation domination, you have tightly coupled baryons, they don't like to cluster, so it reduces the amount of power that you see in the end, okay? There's also little wiggly bits over here. These are called baryon acoustic oscillations, okay? And these are exactly those acoustic oscillations that the baryons are doing while they're forced to move along with the photons. Another prediction we can look at is this one over here, and again there's 3 cases. The light purple one is the one that is preferred by WMAP, or also by Planck these days. The data points here are from Sloan, from a very early Sloan measurement, luminous red galaxies, DR7, that's a long time ago. And again, you see 3 cases over here. Here, what I've done is to fix the baryon fraction to 0.16, which is the WMAP preferred value. Spectral index is against 1 for all 3 cases. Hubble expansion rate is also the same. I have actually allowed the amplitude to be free just to make things easy to see. But what I have varied here across the 3 cases is the total amount of matter that I have in the universe. Okay, so the green line is the one with the least amount of matter. Light blue is the amount of matter preferred by WMAP, and the dark blue line is the one that has a lot of matter. And as we've seen earlier, primarily what the matter density does is to determine this K equality value, okay? Because K equality is defined as the co-moving Hubble rate at the time of equality. And equality depends on how much matter you have. And in fact, we evaluated that earlier in the previous slide. And as you can see, the more matter that you have in the universe, the larger the value of K equality you should find. And that is exactly what we're seeing here. Okay? Less matter over here, more matter over there. So again, I can predict where the power spectrum should turn around. Based on what we saw earlier, okay, this description we saw earlier. Yeah?
Is assuming, because 0.16 you say is WMAP preferred,
yeah,
but it seems like as the x-axis is going to the right, there is some quite consistent mismatch between the light blue line and
here?
the points. Is that because of shortcomings of your model because of the assumptions?
That's actually a very good point. Okay, I will I'll preempt myself. Actually, no, I'm not sure if I have slides to talk about it anyway, but so I'll tell you now. The reason is what is called galaxy bias. Okay, so these are galaxy data points from luminous red galaxies. And one of the things that we do when we use galaxy data to probe cosmology is that we have to make the assumption that the clustering of galaxies traces the clustering of matter. And that is not always true. It's probably, it looks like a very good idea on large scales, but as we go to smaller and smaller scales, we expect this to fail, in fact. Okay? Because the galaxies live in halos, and the halos go nonlinear before the underlying matter-density field go nonlinear. So that's really what you're seeing over here. You have a little bit more power on small scales in the galaxy than in the galaxy clustering than in the underlying matter. This is something that has to be modeled, and sometimes the modeling is maybe not the most trustworthy, but yeah, but it's a known effect. It's not because my linear theory is, well, what I'm saying here is bad or whatever. It's just that the galaxy bias will always force the galaxy power spectrum to tilt up a little bit. Yeah, there is actually also nonlinearities of the nonlinearities developing in the underlying dark matter field as well. Because we're doing perturbation theory here, and perturbation theory will always break down. And the breakdown point is also kind of like around here. So you're seeing a little bit of that as well. Okay, next thing that we can again look at is what would happen if I was to change the Hubble expansion rate. And so here I have again the 3 cases, and but I am fixing the matter density, the baryon fraction, the spectral index, and AS. And if you would recall, in my entire discussion, I never even mentioned what the role of H actually does, because it doesn't do anything. Okay, the only thing it does is to change the, let me see if I can find that slide again, change the normalization of the power spectrum. It doesn't even have a role to play in the transfer function. Okay, so that's why the only thing that you see here is basically just a shift up and down of the power spectrum. Okay, yeah. So that's how things vary with cosmological parameters. Just from pretty much predicted everything. Okay, I think that's all I have to say in this half an hour. Does anyone want to ask anything? You can ask me, ask me to predict what would happen if, or something. Yeah?
It's a little bit not clear to me why it's a blue curve that's preferred, because it seems like data points to the left like blue, but the data points to the right seem to be much more independently with the blue curve.
Yeah, sorry, I'm just, I need to see. Yeah.
Like the clustering of data points at the bottom right,
yeah.
They seem to agree better with the green curve.
Yeah, that's exactly what he was saying before. Yeah, there are several factors at play. The first is the breakdown of the linear perturbation theory, which occurs somewhere around here in the present day time. And the other thing is the fact that we're using galaxies as a tracer of the matter density field. Okay?
I guess it's more so like, I don't know, FB is something we can measure, and that's something that's quite relevant in physics, but you said that H is sort of irrelevant, but it seems to
yeah, but you see, HB is not something we can measure. HB is something we can infer. There's a huge difference between inference and measurement. Yeah, and this goes towards the inference. But yeah, anyway, so the deviation of the data points from the light blue line is really just because at some point my galaxy stopped being a faithful tracer of the underlying dark matter density field. That's one reason a main reason. Okay.
I guess a follow-up question would be: is there any better way to measure it? Is there a better way to measure it where we can get, where we sort of don't use galaxies for this?
Yeah. So there are many ways to try to get to the matter density, the matter power spectrum. You can certainly use, for example, lensing, gravitational lensing, And gravitational lensing essentially is to, okay, so it's called weak gravitational lensing to be precise. And essentially what these surveys do is that they map out a bunch of galaxies, and they have extremely good mirrors that are designed to do lensing. And they know the point spread functions of the mirrors very well as well. And the goal is to look at some slight bit of shear in the shapes of the galaxy. So you might have a galaxy that looks like that. If you have some foreground stuff that's in front of it, then you could actually end up shearing the shape of this galaxy to something like this, as opposed to whatever is its original shape. Now the amount of shearing is tiny, it's percent level, but the thing is that you wouldn't just be looking at one galaxy, you'll be looking typically at, a bunch of galaxies over here, and if they're all kind of systematically sheared by a percent level, then that's your signal, okay? So that's what they're looking at the amount of shearing in each patch of the sky and then correlating it. And a powerful thing about using that as a probe of the matter-power spectrum is that you are accessing directly the matter-power spectrum, okay? Because lensing doesn't care about whether you're being, doesn't really, it's independent of whether you form a galaxy or not. It will just be lensed by whatever is the total matter in the foreground. So that's one of the things that's being done now. There's actually a survey at the moment launched by ESA last year. It's called Euclid. Is it last year? Yeah, last year. It's called Euclid. It's a dedicated lensing survey in the sky at one of the Lagrange points, and they're doing exactly this for a fairly large fraction of the sky. Okay. So that's one thing. So basically these are the two types of approach. You can do galaxy clustering, or you look at lensing surveys to see, to access directly the matter-power spectrum. Oh yeah, that's another one. A related idea is CMB lensing. So the CMB sky is, you got all these little temperature fluctuations all over. And these temperature fluctuations should be Gaussian, okay? Because we expect these things to have been generated during inflation, which generates Gaussian fluctuations. So the CMB sky should also be Gaussian. However, if you look at it in detail, it is not actually completely Gaussian. And that is because you can have the CMB photons, when they travel to us, it's again lensed by the foreground matter. And what the lensing does, okay, so for lensing of galaxies produces a shear, but if you want to describe it in even simpler terms, what the lensing does is that it kind of deflects the photons. So instead of having a straight line, you deflect the photon so that it kind of moves off in a different angle, okay? And that is a nonlinear effect. That generates a nonlinear effect in the CMB. What it means is that if you look at higher order correlation statistics in the CMB sky, you will find something that's some non-zero higher order correlation statistics. Okay? Because if you have just a Gaussian sky, you will only have the power spectrum, and all higher order correlation statistics you might get are not independent of the Gaussian power spectrum. Okay? But if you have nonlinearities generated by lensing, then you'll have a non-trivial bispectrum, trispectrum, etc. So what people have been doing is to look at the trispectrum of the CMB sky and then go backwards to figure out what the nonlinearities must have been to have generated that trispectrum. And from there you can reconstruct something that is kind of like this power spectrum. And that is a nice measurement. It's not really a measurement per se, it's more like an inference again, in that it's the least subject to any nonlinear effects that might happen on the smaller scales. Because you're essentially having, you're basically the photons are lensed at a higher redshift where the nonlinearities were not as large. Yeah, so. Anyone else would like to ask anything? Yeah.
Would you need another transfer function if you had isocurvature?
For isocurvature? Yeah, you can construct a bunch of, well, you have one transfer function that you can calculate for isocurvature perturbations, and then you just multiply that transfer function with the whatever isocurvature extra things that you have. Yes.
Any other questions for Yvonne? If not, yeah, we can thank her.